So we conclude our week of training with the last lecture by Anders.
Okay, good afternoon, everybody. So, today I think you will really see that all these, from the outset, maybe sort of different seeming lectures converge to one point, and I think we can call it a critical point or, deconfined critical point. So last time, yesterday, I showed you that the stochastic series expansion method really works. And I'm going to, discuss a lot of results today. But I do really quickly want to talk to you also about the projector, ground state projector approach. Just a couple of slides to get you an idea. Some of the results I will show you later are obtained with that approach. So that's something where we use the valence bond basis. And I briefly mentioned the valence bond basis before, but I don't really have time to go much into the details that we need to make simulations. Just a couple of things. I also talked about when I talked about the Lanczos method, I talked about the fact that you can project out the ground state from some arbitrary state by acting with a large power of h. So that's what we are doing here. As an example, again, the Heisenberg model, it could be in any number of dimensions. We can write it as a sum of singlet projectors. So this is a singlet projector that projects a singlet between sites I and j. So the Heisenberg model is basically a sum of such singlet projectors. So now we are going to do this approach. So then we have powers of these sums, and again we expand these powers in all the possible strings of the operators, and then we are going to sample these operator strings. So we know that if this n, the number of operators in my string, is big enough, we will get the ground state up to some normalization constant that I call R here, that is completely irrelevant. So now these are all singlet projectors. They are drawn from all the possible bond operators that are in fact singlet projectors now. So what happens when a singlet projector acts on a bunch of singlets, right? The singlet spins paired up into singlets. So let's look at this example of, I have a singlet here from between A and B, and one between C and D. And that's, of course, the singlet. And I use that notation here in the kets here on the left side. Now, there's a sign in the singlet. So we have to be, consistent in our definition, with, where we put, in what order we write these. And in this picture here, the arrow indicates that the sign is like here. So A, B, and I draw an arrow from A to B. So that turns out to be important because that sign structure is consistent with what's something called the Marshall sign rule, which is basically the sign structure of an antiferromagnet on a bipartite lattice. So that's why these valence bond functions where we draw valence bonds between A and B sites, they have the correct sign structure built in. Okay, now what happens when we act? If we act with HAB on a singlet, meaning AB are paired up here, well, the singlet is an eigenstate with eigenvalue 1 of that operator with its minus sign. Well, no, the minus sign is included here. So that's the actual singlet projector, the eigenvalue is 1. But the more interesting thing is if we act between two singlets, like here, then we actually reconfigure the singlets in the way indicated by these red arrows here. So we do get the correct sign structure. This is sublattice A to B pointing, and we get a factor 1/2 there. So these are some very simple rules for what singlet projectors do. Yeah, as I mentioned, it's for bipartite systems. So you can show that if you try to use this on some frustrated lattice, triangular or something like that, you will generate some signs in front of this. So you cannot use it, at least not very easily. But this works quite well for bipartite systems. So now the thing is we can use the kind of loop updating procedure that I told you about last time. We can also use that here if we put the spins back into the singlet. So again, this is a singlet, so you can imagine that you sort of sample the singlet, you pick that one or that one. And then, but what you project out of now, you have some initial state that you project the ground state out of. We can take that to be a valence bond state, and it can even be an optimized variational valence bond state. But here I just show it as a single bond configuration. So then you have an expectation value and you have an overlap, that is like a normalization. So you have two states here, and you project both of them for a long time, and then you overlap them, right? So this is what this illustrates here. So then on the left side you have a valence bond configuration, and you have some singlet projectors acting, and you see this one projects the singlet there, it reconfigures the bonds. Then we have one that acts on a singlet. So these are acting from the right, so we go from left to the right. On this side we have another valence bond configuration. Here we act on the singlet, nothing happens, and here between the singlet. And then you sort of want to put your operator here in the middle. This is a contribution to the normalization. So that gives the sampling weight. And the sampling weight is just 1/2 to the number of valence bonds, because of those rules that I showed you before. And okay, so what do I mean by putting the spins back in? Well, let's keep these singlets here, the bonds, but I pick, you can think of it as random at this point, up or down, consistent with the valence bonds. I cannot have two up spins on a given valence bond. And then these operators, they also become either the diagonal or off diagonal operators that I talked about before when we talked about SSE. So now, that's sort of determined because this was like that. And well, so then this could be diagonal or off diagonal. In this case, it's an off diagonal one. But it all has to be consistent. But it's very easy to make it consistent with the operators at the same location, a starting state. So basically what you do is you sample in this way, in this basis, but then we can go back to that basis when we do our expectation values, because that actually turns out to be a very nice way to measure expectation values. It turns out when you overlap these valence bond configurations, you form some loops, and all the expectation values can be expressed in terms of those loops. But unfortunately, I don't have a lot of time to talk about that today, so I'm not going to talk about the details. Just that, well, one aspect of that is that all your estimators are from the outset rotationally invariant, right? You act on singlets and you work with singlets all the time, even if you sample in the Z basis. So as I showed you last time, if we do finite temperature SSE, we can take the T to 0 limit, but this may actually converge faster if you think of how many operators do you need in this string. If you do the finite T or you do this, you can expect that this should be better because you are only including the singlet sector. At finite T, of course, all excitations of any spin is included. And also you can actually, by sampling a variational state instead of just using a single configuration there, you actually immediately also get 0 momentum. Well, you can easily make such a state. So you basically throw out a lot of states from the Hilbert space from the outset. And that means that, the lowest gap that controls your convergence is not the triplet gap as it normally is, but the singlet gap, which can be much higher. Anyway, so this was just a flavor of what that is doing. And let me show you an example which is, obtained with this method. And that's the 2D Heisenberg model, which Chong has talked about. So you know that it has long-range Néel order, of this kind. But the reason we really know that, as Chong also hinted at, is because of numerics that was done a long time ago. there's no analytical proof, in fact, at least not in the sense of mathematical physics, that there is long-range order. So we look at an order parameter, which is the staggered magnetization, where we just sum up the spins with these phases here. And then, if we aim at showing something about the thermodynamic limit. So we don't break the symmetry, explicitly in our simulation, which you can imagine specifically since we work with the singlets. So we have to look at the squared order parameter and demonstrate that that's non-zero when the system size n goes to infinity. So the method I talked to you about, the projector method, which I'm going to use here, but whatever QMC you use, we work with finite size. So that's why we have to extrapolate. We have statistical errors, but we have no other approximations, right? So, and we have to extrapolate to infinite size, given also the noisy data that we have. So this was first done with these so-called word-line methods by Peter Young and his postdoc, Josef Reger, a long time ago now. And they got this result, that the staggered magnetization is about 0.3, which is 60% of the classical value. If you think of the classical value as what you would have with, classical vectors of length 1/2 or something like that. So it's a substantial order, but that order is reduced by quantum fluctuations. And they did system sizes up to 12 by 12, I think. I could have shown their result because it's sort of fun to compare with more recent. So this is what I got together with Hans Everts, already quite a long time ago now. So here we show exactly this quantity m squared, that's the black dots, but you can also look at just the spin correlation function at the longest distance of the lattice. And if you normalize things in the right way, they should extrapolate in, to the same value as L, this is the linear size as that goes to infinity. And one can demonstrate, analytically that if there is long-range L order, this extrapolation should be eventually linear in 1/L. So you see that it is, and you see that the errors are pretty small, and there's some polynomials fitted there, and this shows the difference between the fitted polynomial and the points. So this is completely consistent with their old result, but you see that because of the better algorithm and of course also faster computers, this is now a much more precise value. And it could be done even better today, but I think nobody has bothered to try to improve on this. I think this is still the best number out there. Okay, now I'm going to talk about JQ model. So let me just quickly say how this algorithm, or both this, finite TSSE and the projector approach, they can very easily be generalized to these JQ models that I have talked about before, where we have some, these are the singlet projector operators. I'm not completely consistent with the notation. Sometimes I call the projectors P and sometimes C, but this is the Heisenberg interaction, which is the singlet projector. And the Q term is a product of singlet projectors on the lattice. And we can demonstrate or at least investigate the nature of that phase transition with these models. So if we take this model, which has two singlet projectors and the J interaction, we have these J vertices that I talked to you about before. We have the diagonal and off diagonal vertices. Now for the Q terms, where we have basically two of these singlet projectors multiplied by each other, if we think of their diagonal and off diagonal parts, there's a part of it which is completely diagonal, like here, but one of them can be diagonal and one off diagonal, and both of them can be off diagonal. So we have these 4 particle vertices that now become part of this network of vertices that I talked about yesterday, but it's actually not much more complicated. So we have quite efficient simulation tools there. Now we have studied the one-dimensional version of this, like Pranay, who is sitting there in the back. He did that to really look at exactly where it dimerizes. So it has the same kind of dimerization as the J1, J2 chain that I talked about before. And sitting exactly at that point, we don't have that annoying log correction that I talked about. So one can look at things like, does it really fit with this CFT description? And in particular, we can investigate how O4 symmetry emerges. Now, when we go to 2 dimensions, which is the more interesting case, these are the pictorial representations of these Q interactions. So this is the Q2 interaction where you have these singlet projectors again, appearing in a product, and you want to sum over all lattice locations and also rotations so that you don't break any symmetries of the square lattice by hand. But we can also make, so to speak, bigger Q terms. In this case, we call these Q3 interactions. And these turn out to have maybe continuous, but at least very weakly first order transitions, as Chong spent some time discussing today. And there were some questions there, if we can also get first order interactions, first order transitions, I should say. And this is one case we looked at a long time ago, where we take 3 of these singlet projectors, but we put them in a staggered, staircase sort of formation. And in that case, we saw a very strongly first order transition. Now we have also done this case and so, some less dramatic, less extreme cases as well, where we had 6 of these projectors. And in that case, the transition is also very strongly first order. No, but I will not really have time to talk. Yeah. Yeah. Yeah, exactly. So that's what mentioned here. So you can combine these in different ways. So for example, well, I will talk a little bit about this, but not extensively. During the conference week, I will give a talk. So I'm saving some goodies for the talk, but I know some of you are not here. So, if you like, I can talk to you more in private after. But Slava's question is exactly like that. So you can take this model, go to its critical point, and then you can turn on, continuously that interaction, for example, and see what happens. And what happens is basically very interesting, but let's not jump too much ahead. We can address that later. So, it's not really true that all the, the models we look at have weakly first order transitions. We can actually go from maybe continuous or very weakly first order to stronger and stronger first order with these models. So today I'm going to give you some flavor of how we are investigating these models, but the focus will be on that model and a little bit about that as well. And I will also show some results. No, they are not breaking any lattice symmetries or any spin symmetries. They have exactly the same symmetries as the starting Heisenberg model, because there's some over all possible rotations, translations, right? And they are singlet projectors, so they don't break any spin symmetry either. Okay, so now in my original lecture plan, I had parts 1, 2, 3, 4, but everything has taken a bit longer, of course, as I also had expected. So now in this last, whatever 1 hour left, I will combine parts 3 and 4, but I think it's basically, the most important things I will have time to talk about. So I will talk about some, principles of finite size scaling, where I also will connect to, the field theory description in terms of scaling dimensions and so on, which are related to the critical exponents. And then I will apply that to deconfined criticality in the JQ model. Okay, so let's first actually look at some data for the JQ model, and then we get an idea of what we would like to basically understand and do with the data. So this is the model I will talk about, and now this will be based on in this case finite temperature calculations, where we scale the temperature as 1 over L, because we expect that the dynamic exponent is 1, meaning eventually you have Lorentz invariance, so we should have same sizes of the system in imaginary time and space up to some factor. It doesn't really matter what you put there for a factor. Okay, so now we need some order parameters. I already talked about the staggered magnetization of the AFM, same as in the Heisenberg model. That's one of the phases of this model. And then we have a VBS phase, and I will really demonstrate to you later on that it's columnar VBS. But for now, let's assume that it is and construct an order parameter for that. So for that we can use, for example, this pi zero sum of S dot S, dimer kind of operators. You measure S dot S somewhere and correlate it to somewhere else. But the actual order parameter, you just sum that up with a minus sign to take into account the the alternating structure of the singlet density. So the singlet density is measured by this operator here. It's on a bond. But you can also rotate this 90 degrees as Chong has talked about. So there's also that dy order parameter corresponding to the other way of doing it. And of course, both of these can be positive or negative, because if this shifts by one step, then you change the sign of that as well, in terms of if these really the expectation values really have alternating values, this will be positive or negative depending on exactly where. So this is a two-dimensional order parameter, and this is the one which has emergent U1 symmetry eventually, that Chong also touched on in his lecture, and I will show that explicitly. Now, bin accumulants are some sort of normalized order parameters that are also dimensionless, so they are very useful to look at first. So these are basically ratios of the fourth power and the second power of these order parameters. And I will later, talk about, why we exactly look at these, but you can see that they are dimensional numbers, and they are constructed in such a way that if you do have long-range order of some type, the bin accumulant will go to 1. And if you don't have order of a specific kind, the value will go to 0. So this US will go to 1 in the AFM phase, and this UD will go to 1 in the VBS phase. And the reason that they look slightly different is that this is a scalar order parameter, and this is a two-dimensional order parameter. So they have a complex order parameter, if you like. So they will have different factors here, as I will discuss a bit later. But for now, just let's look at some data. And this is, what Chong also mentioned today, that state of the art is sort of around 500, in terms of L by L. So these are the two bin accumulants, the spin and the dimer bin accumulant for 5 different system sizes in steps, in factors of 2, so 32, 64 up to 512. And you see that these become, steeper and steeper as the system size increases, because in the thermodynamic limit, we expect them to become, perfect step functions. And you also see that as far as your eye can tell, at least what my eye can tell, these steps happen at the same point, right? So this is fully consistent with a single transition where both these order parameters will vanish. So what we will do with these, these kinds of data is to look at crossing points. So you see that the results for different sizes cross each other around here and here. Yeah. Yeah. Okay, so at the first order transition, you would actually expect to see that this develops a negative dip there. Well, at least the conventional first order transition, this is a little bit subtle, and I hope I can get to that later, but at a conventional first order transition that has a regular coexistence state, the bin accumulants will dip to 0. You will still get 1 and 0, but there will be some other structure around here. Yeah. So as far as we can tell, just looking at these, it doesn't look like it's a first order transition. Okay, we have to analyze carefully and maybe even go to bigger lattices to see what really happens. You can imagine, well, maybe this negative dip starts to come, when I go to system size 2000 or something, but we don't see that now. So of course, the original DQCP scenario would be, very happy with this being continuous, but it's a little bit subtle, as Chong has discussed as well. Well, it actually, if you look at just a scalar order parameter, if you have I showed you the order parameter distribution before for the scalar order parameter. If you have an ordered state, and the system is pretty big, you get that kind of distribution where this is 0 here. If you have a paramagnetic state, disordered state, you just get a blob there. So if you compute, you can even do a simplified version. If you compute, well, let's just assume that the system is very big. These are almost delta functions, and this is a Gaussian. If you have a coexistence, you have basically a 3-peak. I don't know if you can see this. You have 3 peaks. So if you just compute, these kinds of bin accumulants there, you will see that there will be, it will go through through a negative value. And the sharper, those structures become, the more negative will it get. So this is sort of well known in going back a long time. Well, I could do that, look, I cannot show you everything at the same time, right? So this is, something easy to look at first. I will show you some distributions as well. And I will show you a case where it is first order, so you can really see that. Yeah. So be patient, but thanks for your question. Okay, so how do we analyze things like that? So now let me go to more general before we return to the JQ model. And first, I will consider a classical case, but it's super easy to generalize everything to the quantum case. So we know that as we go to a critical point, let me call it the deviation from the critical temperature, I call that delta. So we have a divergent correlation length on either side of the transition. So if you look at some other singular quantity, like order parameter or susceptibility, something like that, it's useful to, so that has some critical form delta to the kappa. Sometimes the singularity applies on both sides, sometimes on just one side, but I just write absolute value here to account for all the possibilities. But if you express delta in terms of the correlation length, so delta is correlation length to -1/nu, you can express whatever quantity, governed by some exponent kappa. So I just use kappa for some generic one here. You can express that in the correlation length in this way. And that's useful because then, if you go to, a finite size, the correlation length is sort of cut off by your finite size. So you can just replace, the correlation length by L here. And by the way, these are things that people initially, a long time ago had sort of found, both in some experiments and in numerical simulations. And later, all these things are explainable by RG. And I will mention some other RG-related things as well. But I guess from Andy's lectures, in principle, you would understand all that, and maybe have seen something about RG before. But it's this, changing of scale that Andy was talking about in the first lecture, and how a system, or how the system on one scale should be related to a system when you look at it on another scale. And here that scale is exactly the system size. So these things can be very initially hypothesized, and now they are known to be correct. So I'm just basically talking about the results. So if you look at the system, close to the critical point, then it turns out you should just take the behavior at the critical point, the finite size behavior, times a function which is a function of the ratio of the two length scales of the problem. Okay. So, but then it turns out that this function is not very convenient to work with. One should actually raise this argument to a power such that the argument becomes delta L1 over nu, and then strictly speaking, it's a different function. And why do you do that? Well, then according to RG, this function will be analytic when x goes to 0. So it should well, it should actually just be a constant that you can tailor. Well, you can tailor expand it, so it should have a constant. I should have specified that more carefully. And then this form also has to be consistent with the thermodynamic limit where there's no system size. So that implies that you have to get rid of this L dependence, and that you can do if this function f, and I call the argument x here, if that's this specific power of x, then you can see that you get from this you get the thermodynamic limit behavior. Okay, so that's basically how finite size scaling works. There will be some other twists later on. So let's look at an example. And now I use the 2D Icing model. It's susceptibility, which can be computed very nicely with these cluster algorithms that I told you about. So now you see, as a function of t, there's a peak which diverges, and the peak height should scale. In this case, let me say here. In this case, this kappa is actually kappa should be minus gamma. I made a mistake here. So this will diverge. So this thing in front should this exponent should be positive, right? So I should say minus kappa is gamma here, and that's gamma is just the conventional name for the exponent of the susceptibility. So that's known to be 7/4, and the correlation length exponent nu that we also need is 1. And in this case, even TC is known exactly, right, from Onsaga's solutions. We know what TC is, and that's what's marked with the line here. So now we can just do this procedure. We can basically take our susceptibility, and we want to get rid of the L factor. So that means in this case, we just multiply it by the corresponding power of L. And then we plot our result versus delta L1 over nu, and we know what nu is. So basically we get the data like that. So now you see I have multiplied my susceptibility by L minus 1 over nu, and I plot versus delta L1 over nu. And I know how to define delta exactly because I know t. So delta is t minus tc in this plot. So now you can see that, at least for the bigger system sizes, the biggest system size is the red point here. These data all fall basically on a single curve, and that curve then is that scaling function. You also see that there are some deviations for the smallest sizes. That's the open circles, that was the smallest size, and those come from scaling correction. So this is not completely correct here. There's some other arguments here that depend on the system size, and they decay as a function of the system size. I will introduce some of that later. Anyway, so you see that this actually works. And now normally we of course don't know what the critical temperature would be. We may know from symmetry what the exponent should be, but even if we also don't know the exponents, all this data collapse can be done as a kind of fitting procedure where you adjust everything until you get the optimal data collapse for your biggest system sizes. Okay, but one can also do things a bit more systematically without looking at whole curves. I want to tell you about some other ways to look at these things. And now we come back to these order parameter distributions that I talked about before. And I will talk a bit more about the Binder ratios and Binder cumulant. So what I showed you before for the JQ model was the Binder cumulant. One can start with something called just the Binder ratio, which is just this dimensionless m4 divided by m squared squared. In this case, from the Icing model. So of course, these in principle can be computed from those distributions, but you don't really need to keep the whole distribution to compute them, but it's useful to see the distributions when you argue about it. So, you know, if you are below TC, any temperature below TC, let's look at this here. These red peaks here would become delta functions eventually. The relative fluctuations will diminish as the system size increases. And that, of course, means, you know, if you compute this ratio for that, you just get 1, right? Now, so that's in the ordered state. If you are in the disordered state, then you basically have a Gaussian peak centered around 0. So to calculate this ratio, you need to calculate 2 Gaussian integrals, which I think we can all do. So then in the case of, you know, a scalar order parameter, if you just have a Gaussian there, you know, you will see that this ratio becomes equal to 3. Okay, so now you can do that more generally for an n component order parameter, and then, you know, what changes is that you know, these Gaussian integrations will be in higher dimensions, so you will get different numbers there. So to get this property that you get 0 in a disordered phase and 1 in an ordered phase, you should use constants like this, where n is the number of components, so n equals 1 for Icing. So these are some results for the Icing model. You know, you can see that it really goes to 1 and it really goes to 0, but when the system is small, there's some rounding. And if you, now you can ask, well, you know, we know what this value is below TC, and above TC, we can say, okay, 0 or 1. But what is it exactly at the critical point? This doesn't tell us, right? Because the distribution at the critical point is highly non-trivial. And in fact, even with Onsager's help, nobody can calculate the Binder cumulant at the critical point exactly. But it's sort of a universal number as well, meaning all, you know, Icing type transitions should have that Binder ratio, and numerically it's known pretty well. And you can see here, when I, you know, blow up this region here, that this is looks pretty much constant, but it's not quite, as you will see in the next slide. So this kind of crossing point analysis, you can see already here that this will be very useful, because you can basically use crossing points as a sort of definition of the critical temperature. But you should really look at the crossing points systematically. So that's what I will do in the next slide. So you will basically extrapolate crossing points. So here is an example of the same thing, but on when I really zoom in more closely at the crossing points, you can see that they actually do not cross in one point. The crossing point drifts, but eventually, if I take 2 very big sizes, the crossing point should take place at TC, and this is the, you know, sort of known numerical value. There's some, you know, error bar on that too, but it's known pretty precisely. So the crossing should eventually happen there. But how about the drift? If we look at system sizes L and 2L, we can see how things drift. So now, you know, the Binder cumulant is a dimensionless quantity. So if we look at the finite size form, there's no L power in front. And that was the argument of the scaling function that we looked at before. But then there are also these you know, scaling corrections that come from the irrelevant fields that are you know, present in the system. So there's some, you know, strength of these in front, which corresponds to how much of the irrelevant fields you have. We don't know what they are, but they should not depend on at least not strongly on how far we are from the critical point. They should not vanish basically at the critical point. So now we can think of this as the smallest of these exponents, and then they become larger and larger, so that these other arguments become more and more irrelevant. So let's look at some actual you know, crossing points of these. So now here I plot crossing points between L and 2L, exactly as I say here. So for example, in between 16 and 32, it would be somewhere there. And between 32 and 64, it would be there, and so on. So here is the vertical crossing point as a function of 1 over L, and here the horizontal crossing point, which is the temperature and the actual binder value, that one. But how do we analyze these things? So you can basically just Taylor expand this function. Just keep the leading one, Taylor expand it for system sizes L and 2L, and set them equal to each other. That's where what the crossing point is, and then you can extract the value of the temperature that I call T star here, where they are equal, and the value of where they actually cross, which I call U star. So then you can try to fit to that, and you should if things well, you should get correct results. So you see that it doesn't really work. This is some form that I fitted. Basically fit these forms with the exponents as adjustables. It doesn't really work for the smallest sizes. This is 1 over L, right? So small sizes here. So then you have to throw out small sizes which are sensitive to these higher order corrections until it works. So here it worked starting from L minimum equals 12, and then the extrapolated TC with its error is like that. And you can see that it agrees amazingly well with the correct value. Okay, so how about some exponents, which are much more difficult than the critical temperature? So let's look at some other observable, and I already told you, what is the finite size scaling form that we expect. And again, if I want to get rid of that on the right-hand side, I put it on the left-hand side. Then I just have the scaling function there. Now we can take derivatives with respect to the distance from the critical point. So if I just look at some at this function, we get an L dependence, and then we get a derivative of that function. Now this derivative of that function we don't really care about. It will be some number, some constant. So if we just look at this quantity here, its derivative, it will be proportional to L to 1 over nu. So that's one way of extracting this 1 over nu exponent. So in the case of the binder cumulant, again, we can look at the binder cumulant, and if I take the derivative, okay, that's the slope of these curves that I showed in the previous graph. Maybe I jump back there. So the derivative, of course, will be the slope, and I can evaluate it at the crossing point, right? So I take the crossing point and then the slope at the crossing point, and I can larger one, right? There are two slopes, right? But I can't take the larger one. And I know how that should scale. So basically the slope should be steeper and steeper, because eventually these become step functions. So then you can take the ratio of two slopes and take the log. And since I do L and 2L, you should also divide by 1 over log 2. Then you get an estimate for 1 over nu. That should hold when L becomes large enough. And this is what you get for the Icing model. You see that, well, let's see, I guess I didn't write the, so now the estimate is on the axis here, and this form should actually be L to minus omega. And so in principle, you can extract omega from there as well. Now this works very well. We know that nu should be 1, and you get something that extrapolates close to 1. The errors become very big eventually, because the relative errors in these things are hard to control. But this is something that people learn always when they learn about finite size scaling, and sometimes it's very misleading to look at the Icing model because it works so well, and it doesn't work that well in any other model. Basically, it's some specific thing about the Icing model. For example, this leading correction here is the exponent is 2, so that means that the corrections go away very fast. Typically, this omega would be less than 1, and it's much more difficult. And even worse, in many cases, you really have to deal with, maybe using two corrections at the same time, because, even the second one may be big enough that it actually bothers you. Yeah. In the 3D icing, omega is around 0.8. It also works really well. So I would say for ON models, it does work well, but it's not as easy as this case. But in other cases, including deconfined criticality, you may have to use two corrections to actually see anything there. Okay, now let's see. Should we take a break now, or is it? Yeah. Okay, let's take. Okay, let's see. I had a question there still. Yeah, so you can associate it with irrelevant operators, like we have heard about the CFTs. Typically they would be just two relevant operators or fields. I'm glad to hear that Andy said that he doesn't know if we should call it, or why we call it operator, because we can also call it field, right? So I sometimes call them fields. But anyway, two relevant fields, but there will be an infinite number of, often irrelevant ones. And if you just take a lattice model and you go to the critical point, well, you have these relevant operators, but then you have, depending on your microscopic interactions, you have some irrelevant fields that you don't control in that model, unless you put in some other interactions. Then in principle, you can control the irrelevant fields as well. And in fact, what some people do is to find models where they can really tune away the leading irrelevant corrections with the aim of getting better finite size scaling. All right, so yeah, so let's take a break then. And how long? 10 minutes or 15 minutes? 15 is fine, right? So welcome back. Let's continue. So now I will present to you my pedestrian way of understanding how the scaling dimensions are related to the critical exponents, and what we mean by relevant and irrelevant. And many of you probably know this much better than I do, but anyway. So if you look at the correlation function, I mean, my main point here is that we are working with lattice operators, not with the actual individual continuum field. So if you look at the correlation function, as we have learned in the lectures, at least for a CFT, we can write that as a sum of powers in the distance R, where these deltas are what are called the scaling dimensions that correspond to these operators in the CFTs or fields. And the lattice operator that we look at hopefully will contain the operator you are interested in. So loosely speaking, the smallest of these deltas, which will correspond to the slowest decaying power law, in this field, we just think of that as the scaling dimension of the operator. But of course, in principle, it can contain many of them. So now let's look at a critical Hamiltonian, and it could be classical or quantum. But for now, think of it as classical, maybe it's easier. So this is I'm sitting at a critical point, and then I add some perturbation to it. So H is just a number, right? And this is some sum of local operators that you use in your Hamiltonian. So, that sum I can call big M. And of course, if we have n lattice sites, I can call that big M, n times little m, and I can write n as L to the D. Okay, so what RG eventually tells us something about is what is the effect on the physics of adding a small perturbation, right, to the critical point. So again, this is sitting at the critical point and perturbing away from the critical point. So again, from RG, this is the form of the free energy, right? So it's L to the minus and free energy density, right? L to the minus D, and then it depends on T. What is T in the critical point? It's T minus TC. and we have discussed that kind of scaling behavior. And now we also have the effect of the field there as another argument. And this mu, y, sorry, you can think of as a 1 over some other nu, but let me just, in RG, it's conventionally called y, right? So now we can get the leading effects from here. It's again assume that this function is analytic when we write the argument in this way. So we can say that the leading effect from exactly at the critical point where this vanishes is just HLY minus D. But now we can also compute this in another way. We can just take our partition function and take derivatives. And then we will see that the free energy scales as h to the expectation value of m. And m scales as L to the minus delta. That's sort of the definition almost of the scaling dimension, how it's connected to a particular operator. I could call that delta m maybe. Well, by the way, you may be worried here because, for example, at my critical point, maybe m vanishes. Well, normally m should vanish. So this sort of looks like it doesn't make sense. But you can go to the next order and then you will see that it will be fine. You can Taylor expand to second order. And if you do that to second order, you get m squared there. So, it's just that you will get twice delta. So now the point is that these have to agree, right? So that gives us this famous expression, y is d minus delta. So at least the way I think of it, I think of delta as the scaling field of the operator, and y as the the scaling dimension of the operator, and y as the scaling dimension of the number that multiplies the operator, which we also sometimes call the field. So the field operator, etc. It's a bit confusing sometimes, the terminology. I'm sure it's because I don't quite understand what I'm doing, but in any case, you can see from these expressions that if you look at let's see, which one should I look at here. So if this argument eventually vanishes, that would mean that it's irrelevant, right? So if it grows with L, it's relevant, and that means y larger than 0. So then you can say, okay, there's some 1 over nu that is positive, that is similar to that nu there, but the value is different. While if the perturbation is irrelevant, this argument there eventually goes to 0, like those L to minus omega I showed before. So in that case, we'll call y, we will call omega. Okay, so if you have a relevant perturbation, of course, it makes the system flow to a different fixed point, whereas if it's irrelevant, you stay at the fixed point. Okay, now let's look at symmetric versus symmetry breaking fields. And now I know in CFT you talk about singlets and higher spin operators and so on. I will just talk about them as symmetric if you don't break any if the perturbation doesn't break any symmetry of your original critical point, and otherwise as a symmetry breaking critical field. Yeah.
Say to the Hamiltonian, you make a relevant perturbation.
Right.
So can you, from the field, from the continuum limit, can you say what is going to happen? Is there a prescription to say what is going to happen in conformal field theory, how the CFT is going to change? You
mean given the scaling, or you mean if you flow away from the point?
Yeah, you have the change to the Hamiltonian, and that is a relevant perturbation.
Right.
So can you, is there a prescription? What would be a prescription to say what is happening in the continuum limit?
That I'm not the right person to ask, but I think the same thing. I mean, you would say the same thing, right? I mean, these things I have written it for a lattice model, but it could also be a continuum, right? This is something completely general, I think. But what you don't know, I think, is if you have a relevant perturbation, so you may get into an ordered state. That's a different fixed point, right? So but something unknown could happen. You don't know for sure, right? So So let's look at again the classical Icing model, as we have heard about, in this during this week as well. So we have the field, the zero field, I mean, here, and we have a critical point at zero field. So in this case, the criticality or the phase transition is caused by a competition between energy and entropy, right? So entropy dominates at high T, energy dominates at low T. So we call T, the thermal field, T minus TC, because it's just, driven by changing the temperature. So if you look at the Boltzmann factor in StatMech, when you change T, you just change the prefactor of E. So you can say that E is the operator conjugate to T. And what you are doing, you are changing the competition between energy and entropy, right? So now if you look at the energy operator itself, the same, this Hamiltonian, that will also decay, if you subtract there may be a constant that you have to subtract, right? But after we have subtracted that, we call that scaling dimension delta naught, at least sometimes we do. And that's how, 1 over nu is defined, the normal, what we call the correlation length normally. But we can also, of course, go through the critical point in this way here. So then we set T to 0 and just add the magnetic field in a way similar to what I just discussed. But, this breaks the symmetry of the model. So this perturbation will be relevant, but it's not a symmetric. So, this we heard about today as well in a slightly different, more precise language, I'm sure. So now we should look at the, Amm correlations, and that defines the scaling dimension of this magnetization operator in the model. And this gives you, an exponent that we can call Ym, but that's equal to some 1 over nu m. So that tells you, when you tune here, how things scale as you go to or from the critical point. Now in StatMech, and a long time ago when people didn't know about scaling dimensions, people wrote and still do the correlation function in this way, the order parameter correlation function. This is the conventional form, which defines eta, right? So that gives us this relationship between the scaling dimension of the order parameter and eta. And eta, of course, is also the anomalous dimension. So normally critical points have one relevant symmetric field, corresponding in this case here to changing temperature. And, often we also have, one or a couple of symmetry breaking fields, right? But we can have multi-critical points, which would have more than one symmetric field. And okay, this is also something that Andy talked about on Monday, but so I don't need to spend a lot of time. But we know that the gas liquid critical point is the same as the Icing critical point. So at the gas liquid, we can take, the order parameter to be the deviation from the mean density at the transition. So here you have some mean density, and if you go, across you get deviations from the mean density. But in this case, you have a symmetry that you don't have explicitly here. You know that, close to this critical point, the same kind of symmetry emerges. But one point that I want to make here is that it's easy here to just tune the thermal field because we have this symmetry. So we know, okay, H equals 0. I only have that relevant field that I'm tuning. But here, if you want to study the gas liquid transition, you know that you have the thermal and the H-like field, but to clearly separate them, you would have to really follow the coexistence line and do some, perpendicular to that line in some sense. But you don't know exactly where that curve is. So it's much more difficult to do it in practice. Right. So, if you just approach in some arbitrary way, you would get, two new exponents that contribute, but you know, at some point one of them will dominate, right? You know, you have two 1/n's, one of them will normally be larger than the other one. They will unlikely be exactly the same. So, but when we study spin models, you know, a good thing is that we normally have this kind of symmetry, like, you know, these other models I've talked to you about before. You know, we sit at zero field and we tune some parameter in the Hamiltonian, which is like tuning the thermal field here. Now, when we go to quantum systems, you know, everything I talked to you about is fine. You just have to replace the dimensionality by d plus z, where in general z is the dynamic exponent, but in CFTs it's even easier because z is 1, right? So you just increase the dimension by 1. Okay, so sorry if that was too sort of hand waving and elementary for you, but at least it's some pictures I have in mind to understand what's going on. So let me give you an example. So let me talk about measuring or computing a critical exponent in a quantum model. And I take the bilayer Heisenberg model, which is very similar to that other in-plane dimerized model that I talked about early on, where we have two different couplings, J1 and J2, but in this case, the layers are all J1 and J2 is between the layers. Now you can also see when J2 becomes large, you tend to form singlets, you know, between the layers. When J2 is small or even 0, you have these Snell-ordered layers. So by increasing J2, you will get more and more singlets between the layers, and eventually you have an O3 critical point where you go to a quantum paramagnetic phase, you know, dominated by those singlets. So this is the Hamiltonian, Heisenberg couplings, all of them. So this has been studied a lot as well, and we know that the critical coupling ratio is something like that. So in this case, you know, we study 0 temperature, so there's no entropy here. So in the classical case, we had a competition between energy and entropy. Now we just have a competition between two different energies, right? This energy and that energy. So you can say that we can drive the transition by J1 or J2. It doesn't matter if you sit at the critical point and then you change J1 or then you change J2, you know, the effect should be the same or, you know, maybe opposite because you move in opposite directions. But the scaling dimensions have to be the same, right, of those two parts of the energy. So what we can do is to look at the correlation functions of the one that is the more convenient, and that's the J2 coupling. So we measure, you know, the S dot S at one bond times S dot S at another bond. So that's the energy correlations of one of these terms, and that decays as a power law. And we know that you know, that power law gives us delta, you know, 1 over r to the 2 delta, so we can get delta from that. And then this y, which should be 1 over nu, if we, you know, because this is the symmetric. I don't break any symmetries when I tune J1 or J2. And in fact, from these curves, and I should say something about the calculation. So this was again this kind of SSE calculations. And we should scale 1 over t, you know, to have the sort of 3-dimensional geometry. 1 over t should be proportional to L. And here I do two, you know, quite different prefactors just to show you that it doesn't matter. Here I do 8L, and then this is 1/2 L. And as a function of distance on the lattice, you see this, you know, quite fast decay. And you may worry that, well, these distances are short. And the reason is that this decay is so fast because you say it's 2 delta. So it's 1 over, you know, r to the, or I call it x here, right? X to 3. And this is the reason why people normally don't do this, right? Because normally the scaling dimensions are such that the decay is too fast to study on long distances. And instead, you know, people extract the exponent 1 over nu using these bin accumulant crossings that I talked to you about before. But this turns out to be, you know, completely consistent with the known value, you know, from classical 3D Heisenberg simulations, or the conformal bootstrap gives, of course, the state of the art result now. So you can look at for example, the paper by two of the people here, and you will see that it's very consistent. So this we did as a sort of demonstration to show that we know what we are doing in some sense. Right, so the point is that tuning this ratio corresponds to the classical thermal field. We tune the symmetric field by this coupling ratio. Okay, now let's, after all this learning what to do and hopefully convincing you that I know what I'm doing more or less, let's go back and look at the JQ model. So now this is a picture similar to the one I showed you before, where we have the bin accumulant of the dimer and I call it UD, and the antiferromagnetic order parameter, which in this case is just measured as the Z component. That's why I call it UZ, but it doesn't really matter at all how you do it. So you see one of them is as a function of G. I should have said what that is. G is in the JQ model, J divided by Q. So this is the VBS phase here, and this is the AFM phase here. And you see that we get these step functions of the two different cumulants, and we can look at the crossing points and the slopes and so on. So
sorry, Anders, can you repeat why you expect all these curves to cross at almost the same point?
Okay, because the bin accumulant itself at the critical point is a universal quantity. It has a universal value. And okay, just sort of naively, I mean, both of them will become step functions and they're rounded by size. So if you have a transition at a single point, they pretty much have to cross each other. What's not completely clear is that the crossing point will not drift up or down with the system size, but it's known from StatMech in general, I guess, ultimately from RG, that, the bin accumulant is a universal number like the exponents that, for a given universality class, you will flow to some number, and that's the number I talked about in the case of the Icing model. So, okay, we don't really, okay, so I should say there are several ways of doing crossing points here. We can look at crossing points of L and 2L for the same order parameter. Then what I said should be the case. We can also look at the crossing point between the VBS and AFM order parameter. That will also cross sort of necessarily, and it will flow to the critical point. We don't know for sure if that will stay at some specific value, or if it will flow to 1, or if it will flow to 0, but most likely it will go to some non-zero value between 0 and 1. Yeah, so thanks, because that's a good point. We can actually look at several crossing points here. So if we do look at, for a given order parameter, we look at L and 2L, exactly like I showed you in the Icing model. Now we can do it for both, the dimer or VBS order parameter and the AFM order parameter. And here I just show, the form L1 over nu that we expect. and here I show when you extract, the slope locally. So for, L and 2L, you can define a local slope, and that slope should go to 1 over nu. I mean, the ratio of slopes, I should say. And you see that it goes to some pretty big value, around 2.2. But it looks like the value is consistent, the same for both of these order parameters. So this would be the conventional way of getting 1 over nu. And Chong mentioned as well that the exponents drift a lot with the system size, but they drift, but they still look like they extrapolate quite a well-defined value. This is just one power law correction to it. The value is pretty big, but if it's a first order transition, in this case, 1 over nu should probably be 4. In the classical case, you know, it should just be D. So here it should be 3. But if we have a coexistence with a gapless state, I think it should go to actually 4. So it doesn't seem to do that. You know, cannot guarantee, maybe actually it will start to go higher. But now we can do it in this other way, right? So in the same way as in the previous slide where I looked at the bilayer and I looked at an energy-energy correlation, here I can also look at an energy-energy correlation. Yep.
Sorry. So how, for the extrapolation, how did you come up with this curve?
Because it's supposed to scale as L to minus some omega.
Right. So you use that.
So we used one single exponent for that, and excluding system sizes until the fit works. So, you know, here the system size is already 100, right? Here I show from 30 to, you know, 400 something. We have 512 too, but I excluded that because the error bar is kind of big. But here you see this is from 100 to something like 400. So it goes, it starts to deviate from the curve if we go more here. But so it's not really true that it looks like the corrections are completely, you know, crazy or something like that. It looks like the corrections are significant, but not crazy. Okay, but the point of this paper here was to try this energy-energy correlator. So in this case, we can look at the correlation function of the Q term. So we sit then at the critical point that we have extrapolated as well. I don't show it here, but we know it quite precisely. And then we look at the QQ correlations, which is an 8-spin correlation, but it can actually be computed. One point is that we have to look at the uniform part of that, and let me not say exactly how we do it because it's a bit involved. But Q itself can also measure the order parameter because this VBS order parameter also can be picked up by these energy terms. But we can extract the part corresponding to the uniform addition of Q terms to the critical point. And we get these power law decays, and this is just looking at either as a function of the largest distance, as a function of the system size. So then X is actually L divided by 2, well, -1 it turns out, and you get this thing here. Or we can take the biggest system where we have good data and just look at it as a function of this X distance there. And you see that the slopes agree with each other. And that gives us the scaling dimension of the operator Q, right? And this is, the one of a new, 3 minus the scaling dimension of that should be this dashed line. And they don't agree precisely, but they agree to within a couple of error bars. So, I would say that's at the very least, well, by the way, the value turns out to be this, which also agrees with this calculation by Nahum et al. That Chung mentioned. Their error bar is a bit larger, but we agree with them within error bars. So that they look at a different model. Well, it's actually not so different because it's sort of taking the idea of loops that we also do in the simulations and making a classical loop model out of that. But anyway, it's the details are certainly different.
Yeah, question.
Yeah.
So at this stage, could you already diagnose a first order?
Not quite, because I will come to that. So you may worry about some bootstrap thing. So okay, so if this is clearly first order, this would go to a value of 3 or larger. That's what it has to do at first order if you have coexisting order parameters, non-zero order parameters. But the value, well, I would say, so this at least shows that we must be extremely close to a critical point. But there's a problem, and this is what many of you here probably know. It violates a very fundamental CFT bound, according to which nu should be larger than 0.052 something. So, it's not consistent with that. You could say, well, maybe, well, actually, it's very hard to. So this is a paper by these 2 Japanese people who well, they did this CFT, numerical bootstrap. And they claim that this is a completely general bound for, I think, all CFTs in 2+1. Or maybe it's in all cases where you have emergent symmetry or something like that. Oh yeah, okay. So the assumption, and this is exactly what Chung said, it's under the assumption that there's only one symmetric field. But then don't ask me about the detail. But I think this is a well accepted result in the bootstrap community. Yeah, no, I may not have represented it right, but I think it's correct to say that it should hold for these systems if there is only one symmetric relevant scaling field. Okay, let me go on and then we can discuss it more, because this is, this is all sort of got, let's say, explained by a new scenario that we have. So the scenario is that the DQCP is actually multi-critical, and that was suggested in that paper. And why do we say that? Well, because we identified a second relevant scaling field, which would, make the bound before be irrelevant, pun not intended, because that was derived under a condition of a single relevant field. So in the JQ model, we have these Q interactions. This would be the Q2 interaction that I talked about before. Now we, and there's some history of this. If I just throw out this, you may say, well, why? But so we can discuss that later. But we looked at this kind of operator. So imagine that you take your critical JQ model, super nearly critical JQ model, and you add uniformly, this kind of perturbation with some, small coefficient. And then you want to ask, is that a relevant or relevant perturbation? So then we can compute the scaling dimension of the operator. We just sit at the critical point, but we can compute the correlation function of these operators that give us the scaling dimension. So we look at some critical point, and we imagine that we add that with some small delta. In the end, we just need to know the effect of that. We just compute the ZZ correlation functions. Now, this is again a bit subtle, because these operators, violate some lattice rotation symmetries as well. So to make sure that we measure the sort of uniform operator that maintains all the symmetries of the lattice, we make a bigger operator that contains several of them in such a way that it doesn't violate anything except, of course, the translational symmetry, because you have to measure a point, but it doesn't violate any of the other point group symmetries of the lattice. And then this actually, again, as a function of the distance, we can measure it in different ways, either on a horizontal or vertical line at largest distance, or on a at the largest distance, or in our biggest system along some axis. And these all seem to be consistent with the same decay. So what one of them looks a bit messy. There's some even odd fluctuation. That's when we measure all distances on a big size. But we can fit one of these branches. And here in this case, I just draw the leading power law, and here too leading power law, but same slope. In this case, I included a correction, but the leading power law is the same in all of them. So I could include the correction here too, but the idea was just to. Yes, exactly. The Z packed into, into a 2x2 plaquette. So, that Z coupling times another Z coupling. It's not turned on, right? We are sitting at the critical point, the presumed critical point. Yeah. So the point is that this gives us, presumably the scaling dimension of the uniform operator consisting of those Z terms. And then we get a scaling dimension around 1.4, whereas the Q operator had a scaling dimension about 0.8, right? So they are quite different. So now we argue that there are two symmetric relevant fields. Now it's a little bit subtle, you know, as all of you know very well. So, you know, we sit at the critical point of the JQ model, which has J and that mod. And I already showed you what the scaling dimension is of that term, which is, you know, part of my critical Hamiltonian.
So of course you want to know how each operator transforms under. So the fact that this operator is symmetries, it doesn't yet goes to the singlet operator of the three-dimensional CFT. I mean, that CFT has many operators.
Well, yeah, that's true. So I mean, maybe it could also be some descendants or things like that.
No, not the descendants. I mean, it could be an operator which has global quantum numbers.
Yeah, maybe some, you know,
in which
maybe
case,
one needs to know more. So, you know,
Yeah.
as far as you know, my understanding is concerned, if I look at some operator that doesn't violate any symmetries of my, you know, critical point Hamiltonian, then it's a relevant symmetric operator. I don't know, you know, the finer points of the CFT, but so I think we have to, you know, postpone that discussion. But you know, I should know more about that. Yeah. No, it doesn't. No, that's the point. So, you know, we sum over all lattice positions and, you know, we pack it into this thing. Because if you look at, you know, just individual ones, you could say, okay, that can also contain the scaling dimension of some operator that breaks the lattice symmetry, right?
But this operator has to have a different symmetry from Q. Because if you had exactly the same symmetry as Q, then you would see, first of all, a power law corresponding to Q, and then on top of it.
Yeah, exactly.
So what has happened here?
So that's sort of the surprising thing too, that let's say that I'm right. I may be wrong, of course, but if I'm right, it looks like this operator only contains one of the fields. Well, you would expect it to contain both, right? This operator only contains the other one, although you would also naively expect that to contain both. So, you know, there could be some reason, or, you know, maybe they really have different symmetries.
They have different symmetries, but you broke symmetry.
Right.
Really.
Okay, but they don't have different symmetries on the lattice.
Well, they have to have a different symmetry. Otherwise they would mix. And you see that there is no mixing. They have a very different scaling.
Okay, you know, that's of course a good question, but you know, as far as I can tell, it could be for some reason that this one contains very little of that and vice versa.
But I mean, how many accidents are you supposed to believe in? You just pick that operator completely out of the blue. And
well, I did not pick it up.
But it has a very different dimension.
It is blue, I agree.
It has a much larger scaling dimension. And in order not to be completely visible, I mean, it has to have a really extremely tiny admixture of that guy.
That's true. So I cannot explain that, but what I can say is that this one violate any symmetry of my other Hamiltonian. Okay, let me go on a little bit. You know, I'm sure your point is very well valid. Yeah.
I just wanted to also just ask. So there's a multi-critical point. So what are the neighboring? I guess how many orders are there now that we're?
Right. Yeah. So some of this I'm going to save until the conference talk, but I will outline for you in a couple of slides what we think is the global phase diagram and you know what phases we have and so on. Yeah. So this at this point, you know, modulus, some major screw up, you know, we have two symmetric fields, and you know, which would of course be beyond the original DQCP proposal if correct. So let's see now how much I have. Like, can I go on 15 more minutes, or is that fine? Yeah. So let me, since Chong talked a lot about the VBS and its symmetry breaking and so on. Let me show before coming back to the issue of the global phase diagram and things like that. Let me say a few more things about the VBS order parameter and how we can check that that has emergent symmetry. Emergent U1 symmetry. So we have the dx and dy components of the VBS order parameter, and Chong showed something like this, but here I have drawn things in corresponding to angles. So we can say that we have 4 different realizations of the columnar pattern, and they correspond to angles in this way. And in some way that should mean, if we call it Z4, it should mean that this one can fluctuate to that one, but it cannot easily fluctuate to that one. And in fact, there are some other VBS-like states at other angles. So if you imagine this square here as a superposition of horizontal vertical dimer pairs, then if you start to add fluctuations to this kind of phase, you can basically go to this kind of phase sort of continuously by adding more and more fluctuations. So we can associate the plaquette state to some points in between there, and this would be my dx and dy axis. So what we can do in the simulations is to measure these individual order parameters, and that's actually most easily done in this valence bond basis that I didn't talk much about, but but then you can see in the DQC scenario, it doesn't tell us what kind of VBS we should have. It could be a columnar or a plaquette state. So that we can check by collecting histograms and seeing if it's a columnar phase, it should have this kind of blobs, and if it's a plaquette phase, that kind of blob. And of course, finite size will broaden those blobs exactly like finite size broadens the distribution of M in the Icing model. But now we have 2 dimensions. So we have amplitude and angular fluctuations of that. So now let's look at some results. So these things, well, initially I have done something in the JQ2 model, but later we have also looked at already some time ago at the JQ3 model, which has a stronger VBS state. So it's sort of easier to see, plaquette versus columnar. So if we take the JQ3 model, but only include this interaction, no J at all, collect the histogram for 2 different system sizes, we really start to see these 4 columnar blobs. And also you see the fluctuation paths, right? So you see that this can really be called Z4 because we are not fluctuating horizontally or vertically, only between nearby blobs. And the blobs sharpen with system size. So it's a columnar state. So this is what I had done already in 2007. If we look at the Q2 model, so only the Q2 terms, then we don't see much of these blobs. Even if we go to a big system, it looks ring shaped. And the simulations are kind of slow. So, here for L equals 128, it's not even a complete ring. But if you, symmetrize using all lattice symmetries, and you just look at the angular probability distribution, you can see that there is some, oscillations, and the dominant weight, which increases with size, is the same as it is here. So it's also columnar. So one can actually use these histograms also to get an exponent that governs the emergent symmetry. Oops. So, in the field theory language, there's a dangerously relevant operator that causes this Z4, U1 to C4 crossover, and we call the length scale of that lambda, and we can actually look at that quantitatively and find an exponent value, and we found that it's something like 1.4 times the normal correlation length exponent. So that was how to demonstrate emergent symmetry slightly inside the VBS phase. And now I think this goes to Slava's point earlier today. If you look at the histogram at the critical point, we don't see any sign of coexistence. We don't only see a sort of rounded circular symmetric shape. These are both close to the critical point. And as Chung has mentioned, using similar methods, one can also, as was done by Nahum et al., they found actually SO5 symmetry by looking at both VBS and AFM order components, a joint distribution of those. All right. So, but now you can ask, this was for the JQ2 model, and I also showed something for the JQ3 model. What happens if you do JQN models with these, many of these singlet projectors? So in particular, you can expect that if you have a really extended interaction in space, that you may nucleate some VBS order and cause a real, strong first order transition. So in particular, you can look at the Q6 interaction. And now in the JQ6 model, you also have an Nel to VBS transition. But in that case, a very strong first order one. And now you really see the coexisting order parameters in the same as I indicated here. If you have a scalar order parameter, you would have 3 peaks. In this case, if you have a Z4 VBS and an AFM, which of course doesn't have any VBS order, then you should start to see 5 peaks, 1 in the middle and 4, the kind I talked about before. So this is basically going from, very slightly on the Nel side of the transition, where you have dominated by this central blob, and then you go towards the VBS phase, you get more and more of these side blobs. And in this case, you are in the VBS and the middle blob is gone. So this is really showing that kind of coexistence state, right? So that means that, well, we can definitely cook up models which have strong first order transitions. And we have also looked at that, systematically for, 2, 3, 4, 5, and 6. And they become more strongly as we increase. And maybe we don't really see this for n equals 2, but I cannot exclude that n equals 2 is first order as well, but very weakly so. So now I think I probably do have time to talk about this as well. So let me look at another deformation of the JQ model, and that was motivated by the Shasta Sutherland model, which I talked about earlier. So it had these 3 known phases. The plaquette phase is a 2-fold degenerate phase, not 4-fold degenerate phase. But then we also recently see evidence that there may be a small spin liquid phase there. I don't know if it can be of the same kind as Chong talked about. I think not, probably. The lattice doesn't allow that kind of spin liquid, but it may be something else. So to really look at these things in detail is hard with the Shasta-Sutherland model because there's a sign problem. So that's why we wanted to see, can we have a designer Hamiltonian for this 2-fold degenerate plaquette state? So then we, at that point, our motivation was also to study, that state going into the AFM and seeing if that was also something that looks like DQCP. So we came up with what we call the Checkerboard Jq Model, which is very simple. So you take the Shasta-Sutherland lattice, but instead of these diagonal couplings, you put Q terms there. So now you can see that this is really amenable to 2-fold symmetry breaking. You can have, singlets forming on those or on those, right? So this is what we studied there, and we found something which was very surprising. So without details, this is just, again, looking at some bin accumulants of the 2 order parameters, and we can see that there's a single transition. We can extrapolate, the value of the transition in different ways using these crossed points. And now we can also look at the order parameters at the transition point. As a function of 1 over L, you see that it doesn't look like they go to 0. This is pretty clearly extrapolating into some non-zero value. So this would be really a first order transition, because we have non-zero coexisting order parameters. But now we had the idea that, okay, let's look at emergent symmetry here. Naively, you would not expect to have any emergent symmetry if you have a first order transition. Like I showed you before, you have these coexistence blobs that are sort of the system just tunneling between M and VBS and no sort of non-trivial coexistence state. But let's just look at this order parameter vector, which has the 3 antiferromagnetic components and the plaquette order component, right? And now we can easily access the plaquette order and the Z component of the AFM simultaneously in the configurations that we generate. So we can make the distribution of M, Z, and P. Okay, let's see what that does. So if we go inside the plaquette singlet phase at this particular value of the coupling, you see that we get a blob on the P axis, nothing on the Z axis because it's in the plaquette phase. In the thermodynamic limit, we should just get a delta function there. We get a blob with finite size rounding. In the AFM phase, we get something on the MZ axis, but it's very broadened. And in fact, if you look at an O3 vector and just project it down to one component, the probability distribution is actually a line from 0 to the size of the sphere. So you can think of this as a broadened line. And you see that these points are very close to each other, and the transition is between. So naively, you would expect at the transition you get the superposition of these two. You should see this one with a PS blob looking similar to that one here. Well, what we see is that statistically this is completely circular symmetric, and in fact it's kind of flat here. So if you take the O4 sphere and bring it down to a two-dimensional distribution, you should get a completely flat, circularly shaped distribution. So that's what we are seeing, except that the radius of the sphere is fluctuating because of finite size effects. Okay, so that is our demonstration of emergent O4, and it's not too different from what Nahum et al. Did for their model, which was at the critical point. But this is not at the critical point. This is in a coexistent state. So this radius does not vanish when the system size goes to infinity. So now we have emergent symmetry at relatively strongly first order transition, which would indicate that in some sense this is close to an O4 critical point, and we have some surviving O4 symmetry on a large length scale, up to L equals 96 at least. Yep. What is the what? The correlation length is so large that we cannot even calculate it. But we have the coexisting phases, but what the correlation length is, it's a bit hard to actually calculate it. So because you don't see a very clear exponential decay. I mean, first these depend on the size, right? And then you should have an exponential decay, and it doesn't look cleanly like that. And maybe that itself is related to the emergent symmetry. I don't know, but I think it's more sort of clear if you just look at the fact that you have coexisting order parameters. Okay, I think this is my last slide now, which is the unified phase diagram. So in the original DQCP, there was a VBS to AFM, generic transition. But of course, we cannot exclude a first order transition there. So I think you can imagine if you have two tuning parameters, that you could have this kind of phase diagram where you have a multi-critical point, I guess tri-critical point separating a first order line and a generic DQCP line. So, then the question is for a specific model, where do you end up? Of course, in this non-unitary CFT scenario that Chung talked about today, and there are many papers. I just mentioned one of the first ones here. The point would be that in these models in our realistic world, you cannot even reach that point. So you always end up just close to it somehow. And what we know with our models, at least, the JQ2 model, must be extremely close because we see, good scaling and so on. But, given that we believe it's a multi-critical point, and also because we have calculated, we have looked at the Shasta Sutherland model, okay? We believe that there's a spin liquid there. We have looked at this model, which we believe, and the evidence is very good, that we have a first order transition with emergent symmetry. Now you can see you can actually combine these models, right? I could just, I could have put the Q terms, here it looks different. I could put my Q terms in these empty squares here, but it doesn't really matter. But then you can think, okay, I can turn off J prime and turn on Q continuously, right? So then go between a spin liquid for the transition. So that would suggest that your phase diagram could be a little different. Namely, it could look like that. So you have a line of first order transitions, and you have a spin liquid. You have a VBS, you have an AFM, and in a particular model, you may cross this line. Like the Checkerboard Jq Model, seems to cross a line like that. But the Shasta Sutherland model seems to cross a line like that. And now if you mix the two, in some way, the spin liquid has to go away and the first order transition has to commence. So a natural scenario then is that there is a multi-critical point there. Okay, now of course, that multi-critical point may also actually be of that non-unitary CFT kind. Maybe that point only exists out in some other dimension or in the complex plane. I don't know. But at least this is the scenario that we are exploring much more, and I will talk a little bit more about it at the conference. Okay, so I think I went over time a little bit, so sorry about that, but I'm pretty much done. So thanks to all of you who have stayed here and listened to my lectures. Thank you.
Any other question? Yes.
You show this emergent O4 symmetry, but it's only a quantitative feature. Is there a way to quantify how good the symmetry?
Can you talk a little bit louder? I can almost.
So is there a way to quantify how good the O4 symmetry is?
Okay, yes, good point. So I only showed you some, qualitative, illustration here in terms of this histogram. I mean, you can look at these angular distributions, very carefully, and see if there's any violation of the symmetry. And up to the system, well, for small system sizes, there are violations. And then as you increase the system size, it gets better and better to the point where it's essentially perfect. And then we cannot go to any bigger system. So what I can tell you is that we cannot see any violations for the biggest size we can do.
So is it possible that in the extremely large system, this O4 is lost?
Oh yeah, I think that's the most likely scenario, because it could be something similar to what we had for the U1 symmetry, right? So in the case of the emergent U1 symmetry, just as an example, we can look at this one, for example. If we look at a pretty small system, it looks very circular. If you just look at it, this looks very circular. But if you look very carefully at the angular distribution, there's some fluctuation, and that becomes worse as the system size increases. And this has to do with this dangerously relevant operator that's, has been predicted for DQCP since the beginning. So depending on what that exponent is, the range of sizes for which the symmetry survives, if you are reasonably close to the critical point, will depend on that exponent, right? So we don't know exactly what that exponent is, but one plan, of course, is to look at that, and then we need to have a model where we can, see also in the Checkerboard Jq model or some deformation of it, that we can actually start to see some violations of this, that we can actually analyze it. But we have actually not been able to, massage this model to give less emergent symmetry, only more emergent symmetry. Well, more in the sense that, it also looks better on even smaller lattices. So, but that would be, of course, important to do. Yeah, please.
So you showed us this two-point function of operator of the two greater Z.
Right.
So you showed us this two-point function contains the exponent, which is that Z does not contain inside any.
Well, it looks like at least it contains a very small amount, right?
How about the two-point function?
That one we have not looked at. So yeah, so you would have then you would say that should vanish in some sense, right? Or uh-huh.
So now we're going to look at already two tools. If you are looking at operator, they contain Q and not, okay,
Right.
it doesn't maybe like five. So the Q doesn't contain something Z.
Right. Well, yeah, I agree. We should look at that one. Right. Well, the only thing again I can say is that we don't violate any symmetry of our original critical point. If in the CFT language it still violates some symmetry, that I cannot tell, and hopefully you can tell me more about it later. But I can tell you we have done a little bit more that we haven't published yet. So maybe I don't even want to tell if in the recording, but I guess that's a record as well. So we can combine these interactions, or we can combine, for example, this Q2 with the Q6. So then we have a critical point there as a function of let's say Q2, let's say J is 1, and Q6. And then we have, here we have AFM phase. Here we have VBS. And, up here we have VBS as well. And then this is connected like that. And we have extracted this phase boundary. And in fact, on this coexistence state, we can also do finite size scaling analysis, exactly like you would do in your, Icing model or whatever. And we see scaling consistent with that being, a critical point. I mean, it could be a little bit, below there, possibly, but this is what we are working on. So I don't want to say, much about details, but, I think this is also what you proposed a bit before, that we should continuously go between them. So yeah, so and then, in this, so this is already what I showed in the last slide, but as I could have, I guess shown it there as well. But then we would have this spin liquid there, if we could go to negative values of Q6, which we cannot, because a negative Q6 would give us a sign problem. So we cannot go to negative Q6, but we can study the mix of the Shasta Sutherland model and the JQ4 model, the checkerboard one, which should be similar. So yeah, so it would be nice to talk to you more about that later, but
Yeah, I was what?
right. What are the what? Yeah, so we could do Q here and Z here, and in fact you have done it, and we see the kind of phase transition here, the phase boundary. But the problem is with that term, you know, we cannot in some sense get very far here. So we always, for example, these bind accumulants that we look at, they change so little that it's hard to do the scaling analysis. So since Q6 itself has a very strong first order transition, we know that, you know, the transition is strongly first order here and goes more weakly first order here. Whereas if we do Q6, you know, there are some changes, but it's just hard to analyze them. The exponents that come out are not very, very good, because in some sense, and you know, that may be because in some sense the, you know, the field is not changed very much when we go there. It's sort of, yeah, there are some mysterious aspects like that. Oh yeah, definitely we have that. So what would you like to do with that?
Well, there's this other kind of complementary approach to sort of variational methods where you impose unitarity, and you can obtain lower bounds on ground state energies, for instance.
You mean for a given model, you can get a lower bound?
Right, right. And so
yeah, so you know, this model, this JQ, you know, family of models, people have tried to do, you know, some variational calculations too, including myself, but it's not very easy to have a good variational, you know, energy for these models.
Mm-hmm.
There's not even a good mean field solution actually to these models.
Okay, so let's thank Anders and all the other lectures for this week.